everyone. In our lecture series based on broadening of spectral lines, we are done with homogeneous and inhomogeneous broadening mechanism. We have also done the examples of homogeneous broadening, which was natural and collision broadening. And we have also understood what is Doppler broadening. Today, we are going to discuss the derivation which is involved, and in derivation basically all we have to do is find the line spread, which is delta omega naught, and then we can get the final frequency distribution. So let's start. Now we know that in Doppler broadening, the width of spectral line that emerges in the spectrum, that is due to the velocity of the atoms or molecules that are moving, and that velocity comes from the temperature of the medium. Thus, we know that different atoms would be moving with different velocities. Thereby, the photons that will be emitted, they would be observed by the detector with some different frequency. The original frequency of the radiation emitted would be different, but due to Doppler effect that we have studied, the detected, the observed frequency would be slightly different. That is all due to the velocity of atoms or molecules involved. Now, let's consider that if nu naught is the frequency of radiation which is being emitted by atom, that is the actual frequency. Due to Doppler effect, we know that the frequency observed by detector would be different. So if nu naught is the frequency of radiation which is emitted by the atom, that is the actual frequency of the photon, then we know that due to Doppler effect, because some atoms would be moving towards the detector, some would be moving away from the detector, some would be moving in different directions. Thus, the frequency observed by the detector would be different due to the Doppler effect, because there is change in frequency due to the relative motion between atoms and detector. So here detector is fixed, but atoms, they are in continuous motion. So relative motion is always there. This nu is the observed frequency due to the motion relative to the observer, and here observer is detector. Definitely both are different. Nu naught is the actual one, but nu is the observed. We know we can relate frequency with velocity. We can mention here nu minus nu naught. Nu is the observed frequency, nu naught is the actual frequency, is equal to V by C nu naught. So this is frequency part, this is frequency part, this is velocity, and this is also the velocity of light. Here this V is relative velocity of atom, relative to what? To the detector. Here we can say of atom with respect to observer or detector, because detector is the one who is going to detect and observe all the photons or emitted radiations. So here it is. Then we have C, which is the velocity of radiation emitted. Whatever photon, whatever is the frequency of photon which is being emitted, the velocity of that photon. Now obviously that photon is also moving. It too would be having some velocity, that is C. So both these V and C, they are velocities. So their dimensions or unit would get cancelled, and we are having frequency and frequency on both sides. So here also frequency and here also frequency left. So right hand side is equal to left hand side. So that means it's totally okay. Next we can write this nu. We have to use the formula now. As we are discussing in terms of omega and not nu, we have done all the derivations in terms of angular frequency and not the simple linear frequency. That's why we are going to introduce the formula. We know omega is equal to 2 pi nu. This implies omega naught if we are talking of, then that would be equal to 2 pi nu naught. That means to the central frequency, omega naught is the corresponding angular frequency. So this is the natural angular frequency. If we have to substitute these values here, this would become omega would be nu can be written as omega upon 2 pi, and nu naught can be written as omega naught upon 2 pi. 2 pi is constant, so that will stay the same, and this is V by C, and nu naught again omega naught upon 2 pi. Since we have 2 pi in the denominator on both sides, so this will get cancelled and we are left with omega minus omega naught is equal to V by C. We can mention this omega minus omega naught, that means it is the difference between the two angular frequencies. Definitely the difference would be small because ultimately the peak that we are going to obtain, some other frequencies that would be associated with that particular spectrum, they would be near one, the one lying closer to the central frequency. That's why the difference is going to be small, so we are going to represent this by delta. We can mention the difference as delta omega, and that is equal to, and here we have omega naught also, so this is V by C omega naught. So that means we have delta omega is equal to V by C omega naught. Next, what we can do is, let's mention this as 1. We will use it further. Now again, suppose the sample is a gas and we are considering Maxwell-Boltzmann distribution of velocities here. Maxwell-Boltzmann law of velocity distribution is the one that we are going to use here, because we know that in a sample, supposedly it's a gas, atoms would be moving in different directions randomly at different velocities. So this Maxwell-Boltzmann distribution law gives us the formula which tells us that how many atoms will be moving with a particular velocity. So by this distribution law, what we get is the probability that an atom has velocity between v and v plus dv can be obtained by this formula. We are getting the expression which tells us that a particular atom will have velocity between v and v plus dv, and that is all understood in terms of probability. Whenever we are dealing with small particles, which are microscopic particles like atoms and even below, we cannot say anything with certainty that a particular atom would be having this fixed velocity at this particular time. No, this is not possible. It's always the probability. For microscopic particles, it's always the probability that we define. We cannot say anything with certainty. So that's why we are using the probability. That would simply give us the idea that a particular atom, what's the probability that a particular atom would be having velocity between these two, v and v plus dv. So there is a limit and we can get an idea what is the probability or how many atoms would be having a velocity between these two limits. We can mention it. This is a predefined formula. Again, if you haven't studied Maxwell-Boltzmann distribution law, then I would make a video on that too. You can refer to that topic. Here, I'm just going to use the expression as it is, because otherwise this derivation would become really lengthy and you have to just memorize this expression for this particular derivation, because we cannot introduce one particular derivation in another derivation, otherwise it would get really lengthy. So here, I'm just directly using the expression, that is square root of m upon 2 pi kt, and then we have this exponential term minus mv square upon 2 kt, and here we have dv, because here we have dv, that's why here we have to mention dv. This always goes. Similarity should be there on both the sides. Next, what are these things? M is mass of atom. 2 number pi is a constant, then k, this is Maxwell-Boltzmann distribution law, and this expression is from that law. So this is Boltzmann constant. So it again has a fixed value. Here we have this Boltzmann constant. This is the value 1.38 into 10 to the minus 23 joule per Kelvin of this constant. Next, T. T is the temperature. Obviously, we know that this whole mechanism, this whole broadening depends on temperature as well, because as the temperature increases, kinetic energy of atoms increase and thus the velocity would also increase. But still, different atom would be having different velocities. This we have already understood. What else we have? Here, this V resembles the velocity, as we are talking of that the probability of an atom having velocity between V and V plus dV. So V is the same thing, dV is the change, that how much extra velocity can get added. So that's why V is already here, we have used it, and dV is also there. Everything is same. M here again is the mass of atom, K is the Boltzmann constant, T is the temperature, and E raised to power minus sign. That means it's an exponential decreasing term. Now, remember this equation 1. We are going to use it again. From equation 1, what do we get? This we can write it as that V by C is, as you can see, V delta omega is V by C omega naught. We can write V by C is delta omega by omega naught, which we can further write as V is equal to, since we are concerned more with the velocity here, C is fixed. See, C is the velocity of radiation emitted. So, one particular radiation that will be emitted, it is going to have a particular velocity. It will move at that constant velocity. The photon, the radiation emitted, they don't change their velocity. They travel at same speed or velocity. It's the atom which keeps on changing its velocity depending on the temperature of the medium and other conditions. So we are concerned with V here. That is the velocity of atom relative to the detector, and not C. C is just going to be fixed. It's a fixed quantity. Radiation once emitted, it will just travel at the same velocity. It will not change. So C by omega naught, and here we have delta omega. Now, if we want to find what is dV, from here, if we take the differentiation on both sides, so C is a constant term, as I told you. This velocity of radiation is going to be same always, and omega naught is also the natural angular frequency, which is constant for a particular sample. Most of the atoms, maximum percentage would be emitting photons of a particular frequency. So omega naught is also constant, but this delta omega, that's the changing value. This is the change. This represents the change. We can mention here C and omega naught as it is, as these are the constant quantities, and here I can write down just the omega to represent this delta omega, as both resembles change. So we keep the terms same. So if I am talking of dV, so that's why I have written d omega. Both represent small change. Now we have to find the probability that atom would emit or absorb, whatever the case is, the radiation in between range omega and omega plus d omega. Here we have this as equation 1. Secondly, the Maxwell-Boltzmann distribution law, it gives us this probability expression. So let's make it equation 2, and here this V becomes 3 and this dV I can use as 4. Since this is in term of velocity PV dV, and we were dealing with this linear frequency or natural frequency in the beginning, but now we have converted everything into angular frequency. Here we will express now this expression in terms of frequency. Ultimately, the spectrum that we will obtain will be of emitted radiation, and the characteristic of emitted radiation is determined by its frequency always. Whenever we talk of emitted radiation or emitted photon, we always talk about its frequency or energy. That's why we can't use this expression throughout. This expression is of no use for us as we are concerned with frequency ultimately to understand the spectrum. So we have to convert this expression, which is in terms of velocity now, in terms of angular frequency. Let's do that. Now I'm going to write down this PV dV in terms of P omega d omega. So let's see how does this expression change. Expression 2. From 2 we get PV dV turns into P omega d omega. Next, this in the square root, all the quantities, these are constant quantities. See, mass of atom is fixed, 2 pi, T is constant, T temperature is also constant because the sample would be kept at a particular temperature. So all these quantities are constant. We can write them as it is, no change. So m upon 2 pi kt. Now let's see the other term. This is exponential term. So e raised to the power minus m upon 2 kt would remain the same because these are the constant quantities after all. But v square, now we have to convert this v square into omega. So now using 3, equation third gives us the value of velocity in terms of omega frequency. We can mention here v square. So c upon omega naught delta omega whole square. This is all in exponential. This is the power of exponent. And then we have this dv also. We have substitution for that. From equation 4, we can substitute for dv. So this thing. So dv is c upon omega naught d omega. So we can mention that. So dv becomes c upon omega naught d omega. So that means we have used both equations. We have used equations third and fourth in second. This is how we have solved it. Now we have obtained the expression in terms of frequency, and that is totally okay because we are only concerned with frequency. The spectrum always gives us the frequency versus the intensity. So intensity is simply the count. Now let's write it down in a proper way. So P omega d omega is equal to C by omega naught. Again, it's a constant term. We can write it here. Then this whole quantity square root m upon 2 pi kt. This is also constant. And then this is the exponential term. So minus m c square. See, this is the whole square. So mc square upon 2 kt. And then we have delta omega upon omega naught whole square and then d omega. Don't forget to put this d omega. Most of the time this is the mistake students actually do, that they just simply forget putting d omega in the end. Always remember, we have to keep the terms exactly identical on both sides. The nature of the term should be same. We have obtained probability now. Next step would be to get the g omega omega naught. After all, it's g omega omega naught which would tell us the line shape plot or profile. In all other derivations, we always found that, but we started with energy of electric field, E omega omega naught, then we found the intensity I omega omega naught, and after that we found the g omega omega naught. But here we will directly jump to g omega omega naught. How? Let's see. The intensity is proportional to probability. We know intensity is proportional to square of amplitude, but intensity is also proportional to probability. though we don't have any exact relation for that. It's a natural thing that intensity is proportional to probability, the probability that we have obtained here. More the probability for a particular atom, since here we are talking of that probability that an atom would emit or absorb the radiation in frequency range omega and omega plus d omega. So if probability is more for an atom, the intensity would also be more. We would expect more atoms to emit or absorb the radiation in that particular range. So that's why they are proportional to each other. That's why we are going to directly write down this g omega omega naught as equal to this expression. That means this probability is nothing but the line shape function g omega omega. A few steps that we take in derivations like this one, it doesn't have any formula behind it. It's by understanding, that we understand that probability gives us the intensity, and probability would tell us that how many atoms would actually be giving away the radiation, like emitting or absorbing radiation in the particular range. So it depends on atoms, and that probability would help us determine the shape of the plot, shape of the spectrum. So here, just by understanding, we are directly putting g omega omega naught equal to this probability p omega d omega. So our g omega omega naught is the same as this p omega d omega. So this is minus mc square upon 2 kt and delta omega upon omega naught whole square. Now remember, this was the probability p omega d omega. That's why we were having d omega on both sides, because whenever we mention that there is some range, and range tells us omega and omega plus d omega. So that's why we were representing this change here. As we are just considering the frequency distribution and we are no longer concerned with this d omega part, so we have removed d omega from here and here as well. Both right and left side, they don't have d omega. Why? Because this is simply the line shape function and we don't need derivative here. We always keep the terms identical on both sides of this equal sign. After all, this equal sign has its meaning. That means both the quantities that we are equating, they should be of same nature. That's why d omega is there on left hand side, it has to be there on right hand side. If we have removed it from one side, then it should be removed from other side as well. These are the things that we should remember. We should understand, we should have understanding of all these things so that we shouldn't make any mistake while writing. Otherwise, this is the portion where students make maximum mistake. They just sometimes cram the expression and they don't know why we are putting d omega or why we are removing d omega, and sometimes people just continue writing down d omega throughout the expression, or they just omit writing d omega in p omega d omega step. So if someone is checking your paper really carefully. Alright, now we have obtained g omega omega naught. Next step is to find g omega omega naught maximum. This is the same thing that we are doing in all our derivations. We want to know what is the maximum value, and then we will find what is the value at half of the intensity. So the value at maximum intensity, the peak, that we represent by g omega omega naught maximum. So that would be, if we take a look at this expression, that would be simply c by omega naught under root m upon 2 pi kt. Why? Because this whole term is a constant quantity. See, it will not change with time. If you see this whole thing, c is velocity of radiation, which is fixed. Whatever is the radiation, it will continue moving with that speed only. Omega naught is fixed. M mass of atom is fixed. 2 is a number. Pi is a constant. Then we have this K as Boltzmann constant. Then T, temperature at which the experiment is taking place, that is also fixed. So all this expression, all this portion, the highlighted one, that's a fixed one. Whereas this expression, the exponential one, you can see due to this negative sign, it's exponentially decreasing term. That means it would decrease with time or it would change with time. And this is particularly exponentially decreasing term. The exponentially decreasing term cannot give us a maximum value. We know that. We are looking for maximum value and this is exponentially decreasing term. That means with time its value is simply going to decrease exponentially. That in fact it will decrease and it will decrease exponentially. So with time this part cannot give us maximum value. That's why we have not included the exponential part in this max value. To obtain g omega omega naught maximum, all we need is the constant, the fixed part, which will stay the same. And we have omitted the exponentially decreasing term because it will simply decrease and it will decrease the whole g omega omega naught itself. Any small value, if you multiply it with any number, it will decrease that number, any smaller number. So if we keep this quantity, this exponential term along with this quantity, then the resulting value would be smaller quantity, would be decreasing one. It would decrease. We don't want that. We want to find maximum value. That's why we have omitted this exponential term. So we have found the g omega omega naught maximum and now we have to find what will be the value of this function at half of the intensity. So let's say that again v omega 1 is the frequency at which the intensity drops to half of the maximum value. So we can write that particular line function will be denoted by g omega 1. We can mention g omega 1 just to differentiate it from this g omega omega naught maximum. So we are saying that omega 1 is the frequency at which intensity drops to half of the maximum value and maximum value is g omega omega naught max. So here the function is g omega omega naught max by 2 as intensity is dropping to half of the value. Now what is g omega omega naught max? That is c by omega naught, this square root quantity. So that means this would become c by omega naught under root m upon 2 pi kt by 2, half of it. That is c upon 2 omega naught under root m upon 2 pi kt. So let's number this one. We have till equation 4. So now let's number it as equation 5. This is equation 5. This is the value of g omega 1 in terms of g omega omega naught maximum. Because we know the value of this maximum, that's why we can easily find the value for half of that maximum. But we also know that g omega omega naught has standard formula, this one. This is the standard formula. And if we are considering now that our frequency is omega 1, so we can modify this formula here. Let's denote this as star. The general expression, if we have frequency omega 1, would be simply replace omega by omega 1. Because any function, if we have to find the value of any function at any frequency, all we have to do is just keep on replacing this omega with that frequency. Because omega naught is fixed. So that means if we have to find the value at omega 1, we will substitute omega 1 here. Then we can substitute omega 2 and so on. Thus we can mention the whole expression as it is simply by replacing omega by omega 1. So let's write it down again. So we are not changing anything else. So c by omega naught is as it is. And then root m upon 2 pi kt as it is. Then you see the exponential term as it is, minus mc square upon 2kt. Now see, here we have delta omega. This delta omega was representing omega minus omega naught term. This delta omega here that we substituted, if we see, this was the expression, and then we wrote this thing. So here this delta omega was representing omega minus omega naught. But here, since we are talking of omega 1 now, so instead of writing delta omega, we will write omega 1 minus omega naught then upon omega naught whole square. I hope this step is clear. Delta omega was representing omega minus omega naught. But now we are talking of a particular situation when our omega is omega 1. So that's why in the expression, all we have done is simply replacing the omega by omega 1. That's why we have written omega 1 minus omega naught instead of delta omega. Let's give this equation a number, and that be 6. This is our equation 6. Here you can see that now we have obtained two values for g omega 1. These two things mean the same. These are same because omega naught is fixed for all. No matter how many g functions you write, omega naught is the same value since the beginning. But it's the omega, other omega that keeps on changing. And here we are talking of g omega 1. So whether you write g omega 1 or you write g omega 1 comma omega naught, that means the same thing. Because omega naught is the fixed quantity. This is fixed. This will always be there. This will keep on changing. That is the one which varies. So one value we have found from the expression itself, and other value we have found from the expression of g omega omega naught maximum, because we know that this is the function at half of the intensity. So that means both these are same. So we can equate equation 5 and 6. So let's equate that. Let's equate 5 and 6. So this is the term that we have obtained from g omega omega naught max by dividing it by 2. And this is the term which we have obtained from general expression of g omega omega naught by replacing omega by omega 1. There are a lot of similar quantities on both sides, so let's cancel them out. So c gets cancelled, omega naught gets cancelled, this whole square root gets cancelled. So that means we are left with, here all we have is 1 by 2. This is 1 by 2, and this is exponent term minus mc square upon 2kt omega 1 minus omega naught upon omega naught whole square. One thing let's do, this is e raised to power minus of the quantity. Let's make it positive. So I'm writing it down like this. 1 upon anything, here we would get a positive quantity. That's why I've written in denominator, because I just don't want this negative exponent here, negative value in the power of exponent, because that creates trouble. So here this e raised to power minus x is 1 upon e raised to power x. This is the rule that I have used. Now if we cross multiply, we get e raised to power mc square upon 2kt omega 1 minus omega naught upon omega naught whole square is equal to 2. Now here we have exponential term and here we have a number 2. These are not equal right now. We want to make them equal. So let's take natural logarithm on both sides. We don't want exponential term. This is a constant number and here it is a exponential term, and that too with positive sign. That means on one side you are having just number 2 and on the other side you are having an exponentially increasing term that might increase if you change any value. So this is not justified. The two sides aren't equal right now. We want to make them equal. Let's take natural logarithm on both sides. So here ln E mc square upon 2kt omega 1 minus omega naught upon omega naught whole square is equal to ln2, natural log of 2. We are not going to solve this ln2, we are not going to substitute any value, we will use it as it is. Now again we have a formula that ln e raised to power x is basically x. This is the formula. That's why, see, whenever we have exponent in our term, we always get rid of it by taking natural logarithm. Natural logarithm removes exponent. So now if ln e raised to power x is x, that means now we have just the power term left. 2kt omega 1 minus omega naught upon omega naught whole square is equal to ln2. Need not to substitute the value of ln2. Next, just keep this on one side and rest of the terms on the other side. So this becomes omega naught square 2kt ln2 upon mc square. Now we have to take the square root. So omega 1 minus omega naught, that becomes plus minus omega naught under root 2kt ln2 upon mc square. Why plus minus? Because square of positive number is also positive and square of negative number is also positive. So that's why whenever we take the square root, we have to put both the signs. Next step. This means we have obtained two values of omega 1 minus omega naught. Let's say one value is omega 1 dash, which is say positive omega naught 2kt ln2 by mc square, and other one is omega 1 double dash, which is the negative of omega naught under root 2kt ln2 by. Now, after all, we are concerned with delta omega naught. We want to find this value because this is the thing which gives us the spread. This is the frequency spread. We want to find this. This is the width in our spectral line. So this is equal to omega 1 dash minus omega 1 double dash. That means omega naught under root 2kt ln2 by mc square minus of minus omega naught under root 2kt ln2 upon mc square. That means we get 2 omega naught because minus minus is plus 2kt ln2 upon mc square. So this is the frequency spread due to Doppler broadening. So this is the frequency spread due to Doppler broadening. Let's substitute whatever we have obtained back in g omega omega naught because we want to know how our final frequency distribution for the line shape function g omega omega naught. So g omega omega naught. For that we need to see what was the expression for g omega omega naught, and that was this one. This was the expression. So it is, so same expression, let's write down. G omega omega naught is equal to C upon omega naught under root m upon 2 pi kt, and then we have the exponent term which is giving us mc square upon 2 kt delta omega upon omega naught whole square. Delta omega upon omega naught whole square. So this is the value of g omega omega naught. Now we have to substitute. Substitute for whom? We have to substitute for delta omega. Now we are going to make a few changes. First, this one here. This I will be writing as delta omega upon delta omega naught. See, we have found the value of delta omega naught and not delta omega. And here in the expression, we have delta omega. So never confuse these two terms. They have different meaning. This delta omega simply means difference between any two frequencies. But this delta omega naught means difference between one frequency, which is natural angular frequency, and some other frequency. So here the two frequencies involved are natural angular frequency and some other frequency, and here the two frequencies involved are some other frequencies. So they are different. Delta omega naught and delta omega is different. So here I'm going to make this change because I know the value of delta omega naught and not delta omega. So just multiply and divide by delta omega naught, and this as it is. So this term would be written like this. Here you can see that we have introduced this new term. Rest of the terms are same. So let's write down. We get C upon omega naught. Again, I don't know what is the value of omega naught. I only know the value of delta omega naught. So here also I have to introduce something. So here I'm introducing delta omega naught. So again, I'm multiplying and dividing by delta omega naught, and rest of the term as it is. So here e raised to power minus mc square upon 2kt delta omega upon delta omega naught upon omega naught whole square. This is fine. I can substitute for here. See, out of these two delta omega naught, I will make substitution for one, and it is always better and easier to substitute for something which is in the numerator than to substitute for something which is in denominator, because if something gets in the denominator, then it might come in the power or something, some inverse change would be there. So we totally ignore that. We try to be simple, we try to follow the easy steps. Just go easy, just solve in the easy manner. So here I'm just going to, because C is constant, and I'm just going to leave this as it is, and I would substitute for this one. I'm going to substitute for this delta omega naught, because all we know is the value of delta omega naught and nothing else. So what is delta omega naught? This is the value of delta omega naught. So let's substitute. That is 2 omega naught under root 2 kt ln2 upon mc square, and then we have this 1 by omega naught also. So like this we can mention. Then we have this term. So again m upon 2 pi kt, and then we have the exponential term e minus mc square upon 2 kt, and next for delta omega naught, again I'm just going to square. So this becomes, for delta omega, I can write omega minus omega naught upon delta omega naught, and here 2 omega naught under root 2 kt ln 2 by mc square whole square. So it's kind of lengthy expression, but we have substituted only for delta omega naught. That's the thing. So I have substituted only in the numerator. So I have not changed the denominator. Delta omega naught we have both in numerator as well as denominator. Here also in the numerator, not here, here in the numerator as well as in the denominator. But I will only change the numerator part. I will only substitute for numerator part. That is the easiest step to do. And we will leave the delta omega naught in the denominator as it is. That's why here we have not changed, we have not substituted for these two. We are not substituting for these two. They will stay as it is. Now let's do some calculations, some more calculations. Let's open the squares wherever we have delta omega naught, and here this is 2 omega naught, and here I'm going to mention that in the square root I will keep 2kt. That's it. Cancel out a few terms and pair up a few terms, and in here in the denominator I have still mc square, and then root ln2 I'm going to write separately, and then I have this 1 by omega naught, and then I have this m, and in the numerator I'm going to write, for this particularly I'm writing 2kt, and then this root pi separately, and this term is there, and then we have the exponential term. See, this is multiplying, and the exponential term says minus mc square upon 2kt. Then we have omega minus omega naught upon delta omega naught whole square. And then we have, now we have to square it. After all, we are just squaring everything. So this portion gives me 2 2s are 4 omega naught square, then 2 kt ln 2 upon mc square. So this is everything in the power of exponent. First, let's cancel out the similar terms. Here this omega naught gets cancelled here, then this 2 kt here. Even here I can write them separately. Let me do that. Root m and root c square. Okay, so this root m also gets cancelled, and then here in the power of exponent, this 2 kt gets cancelled with this 2 kt, then mc square gets cancelled with this mc square, and then that's it. So now let's write down what is left. We are left with c upon delta omega naught, and then we have 2. Then we have this c also in the numerator, so this will also get cancelled. Then we have ln2, then we have root pi in the denominator, and then for the exponential term we have e raised to power minus omega naught upon delta omega naught whole square. And then what else? See, there was this omega naught square in the denominator also. If I haven't mentioned, I should mention it here, because here we had omega naught also. See this term, this term. I just missed it, but it is there. So this omega naught square will also get cancelled, and we have 4 ln2. That means now just arrange them properly. We have 2 upon delta omega naught, and log natural of 2 upon pi raised to the power half square root, and then e raised to the power minus 4 ln2 omega minus omega naught upon delta omega naught whole square. So this is the final expression for g omega omega naught. This is the final one. All remember, substituted only for delta omega naught, and we have deliberately introduced delta omega naught because we only knew the value of delta omega naught, but in the expression of g omega omega naught we didn't have delta omega naught. We either had omega naught or delta omega, but we don't know their values. We only know delta omega naught. That's why we multiplied and divided the whole term here and in the power of exponent with delta omega naught, and we have made the substitution only for the delta omega naught which is in the numerator, and we have left the denominator as it is, otherwise it would become too complex. So we have obtained this final value of our line shape function. which would tell us the, the profile, how the shape of our spectrum would look like. Thus, we have obtained this expression, and delta omega naught is basically the line width. We also say that this is our FWHM, full width at half maximum, and we also call it line width. Now you can see that this expression here, this expression, omega minus omega naught upon delta omega naught, we have substituted this, we have used it as one of the coordinates. On x-axis we have used this value, and on the y-axis we have our g omega omega naught, because rest of the terms are constant. See, 2 is constant, omega naught is constant, ln2, pi, 4, ln2, all these are just numbers. It's just fixed quantities. So only this term omega minus omega naught upon delta omega naught is the term which would change, which would vary. And this value would vary, and then we will multiply it with all these fixed values, and that would give us the value of g omega omega naught. That's why we have made the plot of these two terms. Now this plot, red one, is the one which is obtained for Doppler broadening, and this is a Gaussian distribution. So Gaussian line graph is the one that we obtain in case of Doppler broadening, or you say in case of inhomogeneous broadening we obtain Gaussian plots, Gaussian line graph. It is sharper, it is narrower. Okay, sharper and narrower, of course it's like that. And this blue one is basically the Lorentz line graph, which we obtain in homogeneous broadening mechanisms. That is, in natural and collision broadening we obtain this blue line graph, and in Doppler broadening we obtain the red line graph. Lorentz is also sharper peak, and narrower is also, we can say, but basically it has long tails. So the Lorentz graph, Lorentzian plot, is usually identified by long tails. See, you can see these tails are really long. Here you can see that these tails are really long. This is the only difference. Almost both the plots, they look alike. The Gaussian one is also sharper, narrow, and you see that it just starts and it goes upward and comes down. This portion doesn't go further. It doesn't travel much difference parallel to the x-axis. But in case of Lorentz, you can see that it has longer tails. The wings, some call it wings, some call it tail, they travel quite a long distance along the x-axis. That is the only difference between the two plots. So we say that it's sharper, narrower, and longer tails. So if we have, suppose we say that we are talking of a laser which is helium neon laser, both are noble gases. So if it is operating at room temperature, then other thing is room temperature. So definitely it's quite warmer for the atoms and they would be moving randomly. We know, as we have studied, that natural broadening is the inherent feature of that occurs due to finite lifetime of excited state. So this will always be there. Whether you perform the experiment, whether the laser is working at colder temperatures or even at higher temperature, this broadening will always be there. It has nothing to do with temperature or pressure. So natural broadening is there, which is about, it would be around, here just let me mention, natural broadening in this particular case comes out to be 20 into 10 raised power 6 hertz. Hertz is the unit of frequency, so this much natural broadening is there. And now, as this laser is operating at room temperature, so atoms will be colliding, of course. There will be collision. So due to collision, broadening would be due to collision, the broadening in the spectral line is about half megahertz at around 1 mm of mercury pressure, because we know that pressure also plays its role. Specifically, collision broadening occurs at high pressure gas in high density gas. The Doppler broadening here is very, very large. It's quite larger than the other two broadening. So Doppler broadening comes out to be around 1300 megahertz. And this one is obviously dominating the other two. So see that whatever laser we have under normal conditions, we expect all the broadenings to occur. Why? Because natural broadening will always be there, and it is not that dominant one. It is observed, but still it is the smallest broadening. So you can see that its value is not that much. And sometimes its value is comparable to the broadening from collision. So 20 into 10 is per 6 hertz is the value for natural broadening. Then since laser is operating at room temperature, atom would be colliding. So due to collision broadening, we have obtained half megahertz. And but Doppler broadening is quite dominating. That means lot of molecules, lot of atoms are displaying Doppler effect. That is the change in frequency observed by the detector due to the relative motion between atoms and the detector. And the plot from natural and collision broadening would give us Lorentz line graph, and the plot from Doppler broadening would give us this Gaussian line graph. And ultimately, whatever final spectrum that we obtain is the one which is a superposition of these two plots. We don't see these two graphs separately, these two plots as separate in our final spectrum. In fact, these two plots, they just merge and superimpose to give us the final plot. But the final plot does contain the contribution from all three broadening mechanisms. Each graph shows its own peak. There is peak sharpness and there is line broadening. You can see here also there is line broadening, and here also you can see there is line broadening. So this was all about Doppler broadening, and today we conclude the lecture series that we started on broadening of spectral lines. We have discussed what is broadening of spectral line, then we discussed homogeneous and inhomogeneous broadening mechanisms, and we understood natural broadening, collision broadening, and Doppler broadening with the derivation as well. We obtained the value of delta omega naught, which is the line width for all the three broadening mechanisms. So thank you all for joining me for this lecture series, and if you have any other queries, if you want to watch any video, if you want me to make any new video on any particular topic, you can comment in the comment box. Please put your queries there and let me know how did you find this lecture series and what improvements do you want to include in future videos. Thank you.